And first, I want to go over this quiz. I think it's quite simple, but get used to and go over these quizzes because something like this will be included on the final exam. So you know that we have a final exam. It will be in 3 weeks or 4 weeks, I don't know. But we will have a final exam, and most of the final exam will be about these quizzes. I don't mean it with we're going to have the same questions, but you have to work with PV watts. You have to work with probably with fchart as well, and then you have to do some math, very basic units conversion between kilowatt hours and BTUs and energy and power, all that stuff. So let's start this one. What is the DC system size of a 20-panel array if one panel produces 200 kilowatts at NOCT conditions? Okay, so what is the DC system size? That comes from PV watts. And if we want to do this, okay, so that would be question 1. And the question is, what is the DC size, kilowatts? Okay, so units are important here because one panel is 200 watts. Okay, so this is 200 watts times how many panels? 20 panels. The NOCT conditions, it's not relevant. This is the data we have, 20 panels. One panel is 200 watts, so it's 20 times 200, and this is 4,000 watts, and that means that that equals 4 kilowatts. Okay, so this should be 4. Question 2, how many panels are needed to produce these kilowatts if a panel produces 150? Okay, so in this question 2, it's the other way around. We have a yield of 2,250 watts. Well, I'll do it from the beginning. It's 2.5 kilowatts. This is 2,250 watts. If we divide this by 100, so now 2,250 watts divided by 150 watts, then we have the number of panels, and that would be 2,250 divided by 150. 15 panels. Okay, so that should be 15. Question 3, what is the AC production of a flat PV array with a DC system size of 5 kilowatts in Keene, New Hampshire in January? Okay, what do we have to do? We have to use, and we have all these data, module type standard, fixed open rack, and the system losses. So this is from PV watts. So we have to go to PV watts. We have to go to Keene, New Hampshire. And now what is the DC system size is 5 kilowatts. If we don't say anything, we assume that it's south oriented. So here there is no information about the orientation. So if there's nothing about the orientation, it would be south. So this is 5 kilowatts. This is the DC size. And then I think it's the module type standard. It's a fixed open rack, and the system losses is this. What is the AC production of a flat PV array? So we needed information about the angle. If it's flat, that means that it's horizontal, so the angle will be 0. And now we go to this, and this is the total AC energy production. What is the AC production? In January, sorry, because we have to go, this is the total, in January is 243. Okay, so that will be 243. It's a flat PV array, means that it's horizontal. The DC system size is 5 and all that stuff. Okay, so this is 243. Here we are not asking about units, but the AC production, it's only kilowatt hours. Okay, so be careful, because by default we have these units, but that depends on the unit that we are doing here. Question 4. What is the AC production of a flat, again horizontal PV array? The DC system size is 5. It's in Keene, New Hampshire, and it's in July. So I think it's the same. We can use the same chart here, but now it's July. It's 676 kilowatt hours. Question 5. What is the AC production of a PV array? System size, now it's 10 kilowatts. It's in Keene, New Hampshire. It's in January, and the tilt is 30. And the panels are west oriented. Okay, so here we have to change. We have to go back here. We're in Keene. The DC system size is 10. The tilt is 30. And if it's west oriented, west is 270, this angle. So here we have to type 270. Is this, the DC system size is 10, the tilt is 30, and west. And we're asking for January. So we have to go to results. And in January, this is the production for 81. Question 6. What is the AC production of a PV array in July? So this is the tilt is 30, it's west oriented. So we can go to July, and it's 1,257. I don't know if commas work or not. Let's find out. I think it works either way, without and with and without a comma. Okay, polycrystalline and monocrystalline panels. This is not about PV watts. This is just about basic knowledge about these PV panels. We are talking about this crystalline technology. It can be polycrystalline or monocrystalline. Are more expensive than traditional PV panels? Well, this is nonsense, because those are traditional PV panels. Produce hot water? No, not at all. Are more efficient than thin film? Yes. So there are two technologies: the thin film or amorphous, and then the crystalline. So they are more efficient. The crystalline technology is more efficient than this one. Do not use silicone to manufacture solar cells. No, that's not true, because they do use silicone. So that should be the right question. Compare the yearly AC production of two PV arrays in Keene. So one is, so both are 10 kilowatts, and PV array 1 is horizontal, and the second is west orientation with tilt 40. Okay, so we have to go to Keene. It's 10 kilowatts. The tilt, the first one is horizontal. If it's horizontal, the orientation doesn't matter, but let's use 180. Also, it shouldn't make a difference. So it's horizontal, south 10, and we are asking for the yearly. Okay. So we go back here. So the yearly production is 10,075. 775. Here it's 10,776, and here 775. It's about there should be decimals here, so this rounds up, and this the other one doesn't round up or whatever. But I always have so you can either well, here we have to compare. But even if you have to select the right answer, you can both work. Okay, so this one or that one will work, will be the correct answer. So in this case, option 1 is 10,775, and option 2 will be, what is option 2? Is, okay, west orientation, 40 degrees. So the DC system size is the same, the 40-degree tilt, and the orientation west is 270. And this is 9,820. So in this case, PV array 1 produces more. This is the correct one. No, both are correct. No. Okay, so this is the correct one. The first option produces more. Well, this is interesting because it's not about the tilt. It's about the tilt and the orientation. We know that if they are south oriented, tilt of 40 degrees will produce more than the horizontal one. But with a west orientation, it's the other way around. What is the monthly electrical consumption in kilowatt hours of a light bulb with a power of 50 and it's on for 10 hours per day in a 30-day month? Okay, so this is number 10. What is the monthly electrical consumption? If the power of the light bulb is 50 watts, it's working for 10 hours a day, 10 hours per day. And the month, it's a 30-day month. So it's either April or June, okay, all that. So it's a 30-day month. So the total production is 50 times 10 times 30, 15,000 units. We have watts and hours. So the units are watt, hour. But the electrical consumption, usually it's in kilowatt hours. It's 15 kilowatt hours. The answer here should be 15. And finally, what is the yearly AC production of a PV array with DC size, Hartford, Connecticut? So we have to do it again. It's but now we have to change location. So it's Hartford, Connecticut. The DC system size is 8. What else? 8. The angle is 20 and the azimuth is south. The angle is 20 and the azimuth is south. And they are asking for the yearly, the yearly AC production. Okay, so this should be 10,264. We submit with, and ten out of 10. Great. Okay, so we can go back to the previous one, this one. Review. Which PV array is the best in AC production in Miami, Florida? Both have a 10 kilowatt DC system size. And here we have different ones. So we have the horizontal. So the first we have south, and the angle is 30. It's always 10. Okay, so we have to go to change location. Now we are in Miami, Florida. Yes. And the DC system size is 10. And now we have to run different options. So the first option is south, and the angle is 30. Are they asking for the in AC production? Okay, which array is the best? We don't have any data, so we assume that it's a yearly AC production. So we are working with the yearly, which is this one. Okay, so this option, the yield is 15,772. The second option is horizontal. If it's horizontal, the azimuth doesn't matter, but anyway, so we can go back. So the azimuth can be south, the DC system size is 10, and this is horizontal, so it should be 0. And the total is 14. Yeah, that makes sense. 30 degrees is always better than horizontal. What's the next option? South orientation. South with 45. If we were in Keene, I would say that this is the best one. But in Miami, Florida, I don't think so. So let's do it. It's south, the tilt is 45. And this is 15, 110. Okay, so 30 is better than 45. But what about the next one? Is 15. Is 15 better than 30 in Miami? I'm not sure about the latitude of Miami, but let's find out. So this is 15 now. And okay. So this is south and 15. So apparently the best one is the 30 in Miami, because the latitude, if we can, what is the latitude there? Okay, so the latitude is 25. It's closer to 30 than 15. Yeah, I told you that the best yearly performance is when the latitude is the same as the tilt. Okay, so 30 is closer to 25 than 15. So yeah, just by looking at the latitude, if we are asking for the yearly performance, we should know that 30 is the best. Okay, so we can do this, but just if we are experienced enough, we don't have to do all this. Latitude, Miami, 25. The best orientation is 30. It's not horizontal, it's not 45, it's not 15. If this instead of 15 were 25, let's find out. So if we had here 25, so the last option is south and 25 degrees. Yeah, so this is slightly better than 30. Okay. But in these questions, the best one is 30 degrees. Question 2, which PV array is the best in AC production in Keene, New Hampshire? Okay, so let's try to analyze this without doing anything with PV watts. We have a PV array, south orientation 45. I think this is quite good in Keene. Then we have horizontal, south orientation 30 and south orientation 15. If we are in Keene, I don't have to do anything else. I click this one and I hope it's true. Okay. If you have any, if you're not sure, do it with the PV watts. But for sure, we have horizontal is going to be worse than 45 for sure. Then we can say, okay, is it 45 or 30? Or if when in doubt, you can do the four options and let's see what happens. But I would say that this is without doing anything, without opening PV watts, without doing any math, I am sure that that would be the right one. Which PV array is the best in Hartford, Connecticut? Now this is 40 horizontal, 90 and 15. What is the latitude of Hartford? I think it's around 40 or 40, 41. It's 41. So again, I think that would be the best one. Okay, if they are south oriented, this tilt would be the best. It's better than 90, better than 15, and better than horizontal. So I think this one would be the best. Which PV array is the best in AC in Hartford, Connecticut? Okay. PV array 210 kilowatts. What's the difference between this and that one? System size. Oh, because this is the only difference is the system size here. Well, if we have to compare, it's going to be the same. It's going to be the one with the tilt 40. If we are asking for the value, then we have to do that in PV watts. But if we are just comparing, we don't have to do it. That's if they all have the same DC size, this is going to be the best with the angle of 40. Question 5. Okay, so we're in January. That is, in January, things are different because in January, the sun is going to be very low on the horizon. And well, I'm not sure. Well, if I think and I try to think about it without doing anything in PV watts, maybe I can find the right question. But I think it's faster doing this. So we have a DC system size and we have this tilt. Okay, so now this is question 5. And we have option 1. Well, I can rule out some of the possibilities. The horizontal, it's going to be the worst because if we are working, okay, so let's try to reason. We have a building, the angle in winter is going to be something like that. Okay, so that's going to be the angle in winter. And I'm going to. So the horizontal is not perpendicular. The best angle would be perpendicular to the. So that would be the best angle, around 60 something degrees. Okay. Horizontal is going to be the worst. So let's check the options. Tilt 90, tilt 40, and tilt 30. I'm not sure between 90 and 40. Yeah, let's do this. So we are in Hartford, 10 DC system size. Hartford, the DC system size is 10. And let's try 90. Okay, in January, in 90, we have 985. Okay, so we have 90 degrees. 985. And then the other option was 40 or 30. I think 40 is going to be better than 30. So let's do it. If we have an array here and the angle is 40, what is the AC production in January? Let's do it. Okay, the angle is 40. So let's do it. And it's 980. Okay, so it's slightly worse than the 90, than the vertical panel. So this result makes us think of, yeah, why can't we integrate PV panels on the facade, on the vertical south facade? That's an interesting option for winter. Okay, because in winter, the production on a vertical facade is higher than the production on the optimum angle, which is 40. So that's why we need to understand the use of the building, the schedule of the building. If this building is going to be used from November to February, probably the vertical facade would be the right option. If it's going to be used only in summer, probably 30 would be a better option than 40. Okay. If we're going to use throughout the year, probably 40 is the average best option. Okay, but now this is interesting because if we have to do this, this is not building integration. This is just placing PV panels on the top of a building. When we are talking about building integration, is when we place the PV panels in the facade, and the PV panel is part of the envelope of the building. We don't have to build the facade or the roof and then place something. No, it's something that it's embedded in the construction detail. It's more interesting from the design point of view, and eventually it becomes something cheaper because the same material that we're using for the envelope, it's something that is producing energy. With this option, we have to double. So we create the envelope, we create the roof, and then we have to place something different. If this is integrated into the facade or the roof, from the design point of view, it's better. And from the economic point of view, it would be better as well. Anyway, the right option here was 90. I forgot what I was doing. Question 5 is 90. Then, a vertical window with a surface area of 10 square meters receives a solar irradiance of 400. Okay, so this is math. We don't need PV watts for this. If we are receiving, this is question number 6. If we are receiving 400 watts times 10 square meters. This is watt per square meter. Sorry. Times 1 hour. Now the result is 4,000 units watt hour. If we want to turn this into kilowatt hour, we have to divide by 1,000. So it's 4 kilowatt hours. 4. Okay. Question 7. The solar irradiance on is whatever. What is the total energy with you? So question 7 is the same. We are receiving the irradiance is 100 BTU hour feet square times the area 100 feet square times time, it's 1 hour. And with this, yeah, so the units are BTU. So feet square cancel feet square, hours cancel hours, so the result is BTU. And this is 10,000. 4 zeros, 1, 2, 3, 4. BTU. So that would be 10,000. Question 8. The daily energy received on a roof is 10. Okay, so now question 8. The daily energy is 10 kilowatt hours. So we are receiving 10 kilowatt hours. The surface area is 2 square meters. And there are 10 hours of sun. What is the average solar radiance? So we are receiving 10 kilowatt hour. That means that this is a 10,000 watt hours. And now we have to divide this by 2 square meters and 10 hours. So this is 10,000 divided by 2 by 10. 500. 500 watts per square meter. The daily energy received on a roof is this. Okay, so this is number 9. Daily energy is 50 kilowatt hours. So this is the daily energy, 50 kilowatt hour. The surface area is 10 and 10 hours of sun. So this is 50,000 watt hour divided by 10 square meters. And how many hours? 10 hours. Okay, so this is 50,000 divided by 100, so it should be 500. 500. And finally, question 10, the daily energy is the same. It's the same, but in BTU hours. So this is exercise 10. So the daily energy, it's 10,000, sorry, BTU. The area of the roof is 10 square feet. And there are 10 hours of sun. times 10 hours. So this is 10,000 divided by 100. So this should be 100 BTU hour feet square. Meet. And 9 out of 10. Yeah, I think one of the assumptions that I made was wrong because I've scored only, okay, this is the daily, no, this one. The daily energy receipt.
I don't think you selected one.
I think I didn't select, yeah, I didn't select it, okay. But it's 100, yes, it should be 100. Okay, there are more quizzes, but well, I think these two are so the questions on these quizzes will be on the final exam. Okay, so this I can go over these ones or I can record the video, but I think these two are the most important ones. So from now until the end of the semester, we will have a quiz every Wednesday at the end of the lesson. I will post a quiz and then you will have to answer these questions. And we will keep including different things. Okay, so those are the quizzes. Then I wanted to go over the assignments. The last work, and I think Jacob and Genesis. Genesis, are you there?
Yes.
Okay, do you mind if I go over your assignment?
No, that's okay.
So we have the table of contents. Well, first we have to look at what we were. Yeah, so this was the original table of contents, description of the building, PV watch analysis, and compare Revit and PV. And then we had the passive solar heat gains. I think you don't have the passive solar heat gains, but that's fine. First, we have to describe the building. By the way, I have posted on Canvas. Well, I will show you later because I've posted the details on Canvas. And okay, so this is the original building, and then you have built the angle. Well, if you remember, I did this exercise, okay, so with a tilt of 15 and an angle of 40 here for these 4 rows. And the only thing that I'm asking you is that you're not allowed to use the same numbers. Okay, so you can do this. The angle can be from 10 to 20. You can use 10, 11, 12, 13, 14. Do not use 15 because you already have the results here. So do not use an angle of 15. And here, do not use an angle of 40. You can use 41, 42, 45, 39, 38. Okay, something between 35 and 45, but do not use this combination, 15 and 40. Okay, so I want different results. So that's fine because you have used 20. And in this case, well, you have used 40, but at least you have 3 rows and I have selected 4 rows. So that's why I have more PV production. Okay, so it should be different. If you show me this roof with a 15 angle and this option with 4 rows and the angle is 40, I won't accept it. Okay, so let's use different values. I want you to try different options and maybe you find an option that it's better than mine because this is what we are, this is not a competition, but at the end, I want to see different options and I want to see what option is the best one. Is it 15? Is it 16? Is it 20? Is 3 rows with an angle of 40? Is 4 rows with an angle of 30? I don't know. But you have to show me different options. So don't use this one. So you have the example, and that's the only combination that you can't use. 4 rows with an angle of 40, and this roof with an angle of 50. So you have used this one, and what is the conclusion here? Yeah, the conclusion obviously is that this one is going to be always better than that one. This is the angle 20, 40 volts. Okay, and this is now the PV wall. So we have to compare this result. The yearly it's 185. With Revit, it was 195. Yeah, I think Revit is always too optimistic, but it's close. It's close enough. And this one was 101, and this option in PV watts is 95. Okay, again, they are close. Well, this is not the conclusion. The conclusion is that using PV watts gives better numbers than Revit. It's not better. They are lower numbers, and to be on the safe side, we decide that we are selecting the lowest number. But it doesn't mean that it's better. Maybe Revit is more accurate, but just to be on the safe side, I will tell my client that he's or they are likely to produce a 95 instead of 100. Okay, but better is not the right word. But the conclusions here is about the options. In terms of energy production, the open rack tilted roof at 20 degrees, it's always going to be better than this option. Okay, so this is the main conclusion from the energy perspective. Then if we are talking about money, probably this is much cheaper than this option. Okay, so we are not talking about money yet, but we will start talking about money today when we're using the PVF chart. Okay, but conclusions, it's about comparing, not comparing Revit and PV watts. We have to compare options. So in this case, this option is better than this option. And I have told you before that this was true. They did this. When they were building the TDS center, some of the engineers wanted to do this, and other, I don't know what was whose decision was this. Was it an engineer decision? Was it an owner decision? I don't know whose decision this was, but they decided on this one. And from the energy point of view, it's better. They could have expanded this, and they plan to do it, but this is just this is an economic decision. So why? How many money can we spend on this PV array up front? Okay, so we have money only for 1/3 of the building. If they keep on working with this, probably in the near future, we will see that the whole building is covered by this PV array, so that we can produce all the electricity that we need. Okay, so this is what I want now. This is the first. You don't have the PV, no, the passive solar heat gains. And remember that you have to do this by hiding the curtain wall. Well, at least in 2021. In 2020, you can do this passive solar analysis even with the curtain wall here. In 2021, I think you have to not remove it, but hide it in view, and then you can have the passive analysis. And you have to do this in yearly, in summer, and in winter. Okay, so this is it. That was the first approach to the final project, as simple as this. And now, okay, now I want to start using the PV, the PV fchart. And we're not going to work with this building now. We're going to work with a simple example, with something very simple, a very small building, because this is too complicated. And first we have to calculate the heating, cooling, and electric loads in this building. We're going to do this with Revit, and then we will use a PV fchart. Okay, today I'm going to show you how to work with this PV fchart with a very simple building. Don't save. Well, first I have uploaded here details. So if you open these details, we know that because we have studied this detail in other courses. If you haven't seen this yet, okay, so this is the TDS building roof to wall transition. We have different details. We have this one with the concrete walls, with the concrete blocks, sorry. And we do have files. No. This is detail 1, detail 3. Okay, this is, you know that we have curtain wall, so that would be the south elevation. This is the roof, this is the curtain wall, triple glazing, as you can see. And then we have these weird shapes. Why do we have this? Is it because just the architect liked it, or does it have, it's like a louver so that it protects the glazing from the summer sun? I would like to believe that the latter is the correct thing. Okay, so they have extended this so that in summer they can protect this glass from the sun. I think it would be a good option, and this is something that we can analyze with Revit. Okay, so we'll be working with these details in Revit and Therm to analyze if they are good enough or they can be improved or whatever. So this is another detail. And here we have a section. Okay, so this is the detail that we have just looked at. This is the roof, this is the curtain wall, this is the grid space. You see, I don't know if you have noticed that we have some elements here. Those are not columns because this part is hanging from this. Okay, so, well, that's interesting from the structural point of view. But well, we can analyze these callouts, this with Therm, and I think we will run a solar simulation with these elements to see if they protect this facade in summer. Anyway, you have the details here, and now we have to analyze these details, or maybe we can improve them, but we will see. You have those details here, and you have this file, and this is the example that I'm going to show you today, this loads PV fchart PPTX. It's not completed, so today I'm going to open this, and I will complete it with the PV fchart, and then I will upload it again. We are going to analyze this building. You know this building, Matthew? We are going to analyze this building. It's just very simple. It's not a cube because this side is slightly bigger than the height, but it's a rectangular building. And we have PV integrated panels here. And then we have a roof in which we have to place the PV panels. And the goal is to create a zero energy building. Okay, so first we have to analyze the loads, and then we have to analyze how many panels we need to turn this building into a zero energy building. First, we have to analyze the loads, and this is something that you should be able to do, okay? Because we have done this, at least we have done this in systems. You remember that in systems, we prepare the schedule with an Excel file, and with that schedule, we can do it on a monthly basis or whatever. I have done here 2 examples in January and July. So we know we have indoor temperature, we have outdoor temperature, we have the number of people, and then we have the loads through the envelope. So this is the U value of the roof times the area of the roof, the area of the walls times the U value of walls times area of walls, U value of floors times the area of the floor. And it's always indoor minus outdoor temperature, or interior minus exterior temperature. And here we have the glass. We have glass, and we have the U value of the glass, the area of the glass, indoor minus outdoor temperature. When we are working in winter, we always use this. Oh, and here we have ventilation loads. Okay, so we need the number of people. We will need the CFM. CFM, as I told you many times, it's always 20. So we have to multiply the number of people and times 20. And then ventilation loads is about sensible heat and latent heat. So I'm not going to explain it now, but probably I will explain it any other day. But we have to calculate the ventilation loads, and it depends on the schedule. From 0 to 6, the building is not working. From 8 p.m. until midnight, the building is not working, and this is the operating schedule. And this is the number of people. Okay, from 7 to 8, someone turns on the heating system. There is nobody here, but the heating system is on, so that by 8 there will be there will be a comfort temperature here. And then we have people to people, 4 to 4 to. That's very small. So this building, there should be up to 4 people because it's very small. In the TDS center, as you can imagine, the schedule is going to be a little more complicated, especially because of the number of people. So we have to make up something for the spaces we're analyzing, and we have to analyze how many people there will be there. This is winter in January, and in July we have indoor temperature, outdoor temperature, number of people. The schedule is the same, so the number of people is the same in January and July. Here we have the heating loads through the envelope, the heating loads through the glass, the ventilation. But in July, in summer, we have to add internal loads. Okay, so internal loads and solar radiation. Because in winter, if we are not on a cloudy day, we don't have any sun. So again, to be on the safe side, we don't take into account the sun that is entering the building, because that will reduce the heating load. But in summer, it's the other way around. We have solar radiation entering the building, and this is adding cooling loads to the building. Okay, so we have the loads through the envelope, ventilation loads, and we have solar radiation, the energy that enters the building through the glass. And finally, we have internal loads. Internal loads is about the people working on that building. If we have just 4 people, it's not going to be relevant. But if we had 100 people working on that building, or if we had a gym with fewer people, but all of them running or sweating or whatever, probably the internal loads will be more important. Anyway, you know that in fchart we can upload or we can type loads by hour. So this is what I want to do here. Okay, so I have done this with this schedule, and now we have a schedule, and we have the loads in winter and summer every hour. So we're going to upload this on the fchart, these values and these values. And finally, this is the yearly heating, cooling, electric loads. Okay, and here we have this in kilowatt hours. And this is, we can get this with this Excel file. Okay, so you remember that we ended up with a graphic like this. And here, if we are calculating this every month or every year, or yeah, no, every month, here we have the walls, the area of the wall, the R value of the wall, the roof. Here we calculated the heat losses and heat gains through windows. And here we calculated the ventilation and infiltration. And here we calculated this on a monthly basis. So we will have this chart here. Okay. In this building that I have been calculating, this graphic in January, February is like this. Okay, but we can get this information. We will get all this information, the schedules, the daily schedule, and the yearly electric loads from Revit. Okay, so next week or this coming Wednesday, I don't know, we will calculate this with Revit. We can do that. And then when we have all this information, then we can go to the PV fchart. And this is what we're going to do today. So this is the month, and this is the electric load. Here we have the graphic, and here we have a table. You see that in January, it's 563. That comes from, this is almost 200, and this is 300 and something. The positive are heating, and the negative are electric and cooling loads. But since everything is electric, this is going to be around 500 and something. Okay, so in February it's 369. If you look at this is almost 400. Yes, so that would be 659. In July it will be around 500 and something. It's not 600, so it will be in July 543. Okay, so this is the table. These are the actual numbers, and this is the graphic. We need both because in the graphic we can understand, I think visually, we can understand it better than here. At least I can understand, because here I have to analyze 500, 300, 400, whatever. Here, just by looking at this, okay, what is the maximum, what is the peak load? Okay, it's going to be either in July or August with 500 and something. Yeah, in August is slightly above. This is 554. This is 543. Yeah, so kind of. Okay, so we need this graphic. We will take it from Revit. We need this table. Probably in Revit we can get this table as well. And now we need the panel, the PV panel. So this is the panel that we are using. I think this is this is the Canadian one, not the Chinese. We are using this panel, so this is the length and the width. This is the area, 1.669, 1.67. And these are all the features of the panel. Maximum power is STC, the nominal operating cell temperature. Okay, so we have all this data. And now we're going to work, because before using the PV watts, the fchart, before using the PV fchart, we are going to use the PV watts just to analyze different options, because on the PV fchart we can test things. We just need to, and introducing all these loads is going to be something exhausting, okay, and we are going to do it. So we better use something simple. A better tool to this first analysis could be PV watts. What are we going to do? We're going to test different options, and we're going to see how many panels roughly we need to create something similar to a zero energy building. And then we will do something more accurate with the PV fchart. So this we're going to use on PV watts. Okay. After describing the building, by the way, this is south, north, east, and west. So all the panels are south oriented. We describe the panel, the features, and then we are going to use PV watts just to understand what we are doing. So the first option, option one, I'm going to use 6 panels. The production of each panel is 320. Okay. So the total production is 320 watts per panel times 6 panels. So this is 1920 watts, which is 1.92 kilowatts. And I'm going to start, this is in King, in Hampshire. So I'm going to start with 45. The angle is 45. And this is the DC system array. Okay, so let's do it. We are going to open PV watts. We are going to change location. We're going to King, Hampshire. And now, what is the system size? The system size is 1.92. 1.92. What is the angle? 45. And what's the orientation? 180. Do it. And now we have to compare just this, the AC production. Okay. Is this a zero energy building? Not really. In January, we are consuming 500 and we are producing 192. In July, we are consuming 500. In August, 554. And here we are producing 200 and 240. Okay, so this option one with 6 panels at this angle, this is not a zero energy building. Okay, so what's the conclusion of this? It is not a zero energy. Are we, and I'm going to make it red. It's not a zero energy building. Okay. Well, first, I think we need another data here. Yeah, because we want to compare the total as well. Yeah, it's a shame that they don't have this. Okay, so let's do it quickly. 563 plus 369 plus 48 plus 449 plus 461 plus 499 plus 543 plus 554 9 10 3 8 and 3. Okay, so this total is 5,451. Okay, so if we are designing a zero energy building, this number and this number should be similar. And now they are not. Okay, so if we analyze the monthly production, we see that we are far from this. And if we analyze the total, the yearly demand, we are like half. Yeah, so we have a lot of room for improvement. Okay, so option one is not best. So we'll try option two. We need more PV panels. So 6 is not enough. So let's try 12. So 12 times 320, it's 3840, which is 3.84. Okay, so now the DC system size, it's 3.84. The angle is 45, so it's a good angle. It can be maybe 44 is better, or 43, but 45 it should be good enough. We have to use PV watts again. We are in Keene, New Hampshire, and the DC system size is 3.84. The angle is 45, the azimuth is 180. And now the PV production well, we are getting there. Looking at this number, it's 5,400, and this is 4,900. We are getting there, yes. It's not a zero energy building yet. It's not a zero energy building yet. So let's try option 3. It's not a zero energy building, but we are. What can I do now? Let's try 14 panels times 320. Okay, so now it's 4.48. And now let's go back, change this 4.48. And okay, this is option 3. Okay, now it is a zero energy building. It's a zero energy building because we are producing slightly more energy that we are consuming. But now there's a, yes, so as you can see, in January, we are not producing as much energy as we are consuming. And in July and August, we are producing more. In August or September or October, we are producing more energy that we are consuming. So here we have the balance between the energy that we need to buy, because here we need to buy the energy in January, but in August or September, we can sell energy to the company, or we can supply this energy to the grid. Okay, so with this, we have a, yeah, so we can finalize our report here. We can say, okay, so how many panels do you need? You need 14 panels at this angle, and it's quite good because even if you see the energy that you need and the energy that you produce, it's quite close. Okay, so I think this is a good option, and this is a zero energy building, but we want more. And now we're going to use the PVF chart to find out more. Okay, because that would be enough, but we want to be here. We don't have any think about the economic aspects. We don't know the initial investment. We don't know when we can return the investment. We don't know on a daily basis what happens with the energy that we sell and the energy that we buy. Here, we can see that we need to buy energy in January and we can sell energy in August. But okay, we need to know more. So we are going to use the PVF chart. Be careful because we need to use the PV, not the F chart. Okay, the PVF chart. There you go. We have these economic parameters. We are going to use economic parameters, but we are going to leave this with this default option. Here we have the cost, the period of economic analysis, 20 years. Yeah, that's always good, analyzing this in 20 years. If you have a client, I know the client is 50, a 20-year analysis, I think it's good. If you analyze a 50, if you have a 50-year analysis, your client might expect that after 50 years, well, maybe they are not on the on that earth and they are living a better life. We don't know. But 20 years is always good for this kind of analysis. Everything that is above 20 years is like 20 years is good. What about the down payment? Well, the down payment depends. And then what about the mortgage? We don't know. If you are studying construction management or anything related to business, that would be a good question. Okay, so you are analyzing this in this course from the energy point of view, but is it better a 10% down payment or a 20% is better and we reduce the mortgage, or what is the discount rate, the annual market discount rate? Okay, so what are these numbers? We're not going to use it. We're going to use this default option. I understand that this economic period is fine. In terms of down payment, I don't know. The more the down payment, I think well, depends on the inflation, depends on that. And anyway, if you are working with construction management teachers or you're working with business, you can try to find out what the best options we'll have here. Okay, so in this course, we're not analyzing this economic. Well, we are analyzing the economic results based on these inputs. But, well, let's work with this. We know the location, it's northeast, it's in Kin. And now we have to work with all these, the cell temperature at NOCT conditions. And we have all these. So here we have the characteristics of this. The nominal temperature at this condition is 47. It's not 44, so let's add here 47. The array reference efficiency, it's the module efficiency, it's 19 point. Okay, so here we can type 9.19. The array reference temperature, I don't know if we had this here. Sorry, thermal. Okay, this is the operating module temperature. We don't know. We don't have this array reference temperature, but 28, it's fine. Array temperature coefficient, we do have this. The temperature coefficient is 0.47. So this we can say that this is 47. The power tracking efficiency, we don't have a tracking system, so you can leave it. And then this, okay, and this is now the array area, number of panels times panel area. We were in option 3, so we have 14 panels. What is the area? Here we have the DC system size. We have multiplied 14 panels times the production, but now we have to multiply this times the area of one panel. And the area of one panel is, well, 1.67 square meters. So this is times 1.67 square meters. Okay, so this is panels times 23.38. 23.38. Okay. So the area of the panels would be 23.4. The slope is 45, and the azimuth south, in this case, south is 0. Do not type here 180 because 180 is so we will need this reference where the south is. Okay, so this is the characteristics of the panels that we are working with. Now we need to work with the system. If we have this utility interface, we don't have a battery storage and we don't have standalone. We're working with the grid. Okay, so this is grid connected and that's it. It's a flat plate array, so we're not using this CPC and we're not using any tracking system, so we're using these options. So let's check that we have by default, we have something connected to the grid and we have the flat PV array. Check it. The weather, we can check that we're in the Northeast. We have already selected that. And now this is the painful thing that we have to do. This is the load. Okay, so as you can see, we can work with January, February, every single month. We can change them all. And here we have the schedule. And now we have to try to do this. Okay, so we have this option in winter. And we have the same option in summer. So let's, yep.
Do you know if there's a way to like import that data into the program instead of just having to put it in manually?
It would be great if there were, but I think there's a way to import things, but probably in the full version. This is the demo version, and then it doesn't work. That I try to do after doing this. First time we have to do it by hand. The second time maybe it's easier, but the first time you have to do it. Okay, but it'll take 5 minutes. I mean, sometimes you say, oh, it's boring, I can't do that. And it takes 5 minutes. So think about what you do in 5 minutes. Probably it's worth doing this. Anyway, from 0 to 6, this is 0. 0. Even from 0 to 7. Then from from 7 to 8 is 889. So we can copy 889, or we can type it. So this is I'm going to save it, but I want to So we're in load. Okay. So this is 1063. 125 967 4 842. And then after 8 p.m., it's 0. Let's save it and let's view the load again. And now all months are the same. Okay. Here we have data for July. So we can go to July and well, we can do the same. So here it's 91, 307, 394, 5. Okay, and now I change the load again. It would be wonderful if we could copy this, but unfortunately we can't. We can do something. We can always.
Type in something in here?
Sorry?
Type in something in here?
Yeah, sure.
Thanks.
You can always save the load file. And this is on desktop, PDF chart. Okay, so let's call this one example 1 and save it. Okay. So once we have this, we have saved that file. Even in this version, in the demo version, we can open load file. And if we open a load file, it will have this example. Okay. So at least if every time you do something like this, you save it, well, at the end, you will end up having something accurate. Okay. But well, first time is it's boring because we have to do it. I have done it in January and then I have done it in July. In theory, we need one of these tables, one of these charts every single month. Anyway, it's a question of time. You know how to do it. So if we will go to January, then if we have the February one, we have to do it. If we have the March, we do it again, so on and so forth. So this is not going to be very accurate. Let's see what kind of results we get. but it's a question of time. It's a question of having tables and just spending like a couple of minutes doing this on a monthly basis. And then you can save that load. And if you have to fix something, okay, at least you can save the load, and then you can change slightly or some of the numbers that you have gotten in other simulation. Okay. So we have, well, the preferences, we have international units, the system, we have utility phase, flat plate array, the load, we have changed the load, the weather, we have selected the Northeast, we have done all this, okay, we have selected all this data from the PV array, and we have all these economic parameters, and we can run and calculate. And it's pretty easy. Okay, so those are the results. And now here we have all this information that we might need. We have this information in a January day, on a January day, on a July day, and we have this information throughout the year. And what is this? Okay, so this is the load. As you can see, this load is always the same. It only changes when we have 31 or 28 days. In February, we have 28 days. In January, we have 31 days. Is it exactly the same load that we have gotten here? Well, in February, it's quite similar. It's 369, and this is 358. In March, this is 408, and this is 397. In July, I did something wrong here because in July it should be more. Yeah, so probably I have done something wrong. But as you can see, if we look at the electric load here and we look at the electric load here, there, they should be similar. So it's similar in, not in January, because in January is 500 here and this is 396. It's similar in February, but then in July I did something wrong. I mean, these data are not feasible because they should be twice as much as this one. Okay, so I can go back to load. I can change the load in July, and let's make it much bigger. So let's make it 100. I calculate it again. And now loads in July are getting better. So this is 425 and should be 540 something. Okay, so we have to adjust this. I told you that this is painful because we have to make sure that this data, well, I have just selected a day. Maybe this is not the day in which we have the highest load. And this is what happens. Maybe I have selected a cloudy July day, and in this day, the cooling loads are lower than the average. Okay, so that's why we have to, well, we can do something different. Imagine that we have this, and this is the monthly load. What is the load in July? It's 543. Okay, so let's do this. So in July, the load is 543. How many hours? What is the working schedule in July? Okay, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 hours. Okay, so if this is 543, these are kilowatt hours. So that means that this is 543,000 watt hour divided by 13 hours. That will be 543,000 divided by 13. It's 41,000. No, sorry. This is on a monthly basis. Okay, so we have to divide this by 31 days times 13 hours. There you go. Now, this is 543,000 divided by 31 divided by 13. Okay, so yeah, that makes sense. Every hour is 1,347. Okay, if we are doing this again, if we change the load view, it's not so accurate because it depends on the occupancy, but we can say that every single day we have 1,347. And then we can copy this. And then, okay, we run and calculate again. And now this load in July, it's 542. And the load here is 543. So we are very good. Okay, so maybe this is a different way to do it. If we are doing this in July, we can do this in different months. Like in August, ours would be 554,000 divided by 31 days, right? Divided by 13 hours. So this is 554,000 divided by 31 divided by 13, and this is 1374. Now we can go back to the load. We can go to August, and now we can 1374, and then we can copy. And then, okay, I'm going to save the load file. Okay, so now if we calculate, at least July and August are similar, and other months are similar. So it's a question of trying to adjust the data that we have here from the simulation and the data that with the load that we are getting with the PDF chart. And now we can work with this. So this is the energy that we need to buy in January, and this is the energy that we sell, and this is the energy that we buy. Why? Because even in the same day, I need to buy energy, and there will be other moments during the day in which I will be selling energy, because it depends on how many solar radiation, how much solar radiation we are getting in our building. Okay, so I think this is good because in every month you see how much energy you need to sell and how much energy you need to buy. And then we have the economic analysis. In the economic analysis, the most important thing is the cash flow. And well, this is what I want to look at, or this is what my client would like to look at. You see that we have negative numbers, and there's a moment in which this negative number turns into a positive one. So this is the moment in which we start making money. When does it happen? It happens in 1, 2, 3, 4, 5. At the 6th year, we start having a positive balance. So that means that at the 6th year, the payback period is 6 years. And 6 years is something very reasonable. Everything that is below 10 years, your client will accept. Because 6 years, okay, so I make an investment right now, I make a down payment, then I have a mortgage, but in 6 years I start earning money because I'm saving energy. And the balance between the energy that I buy from the grid and the energy that I sell, it's also positive. Okay, so that's the economic analysis. But of course, this economic analysis comes from this. It depends on the down payment. It depends on the mortgage interest rate. All these things that we don't control. So that's why if you have a business advisor and you have feasible numbers here, then you can have a more accurate. But I mean, those numbers by default, it will be quite good. So with this analysis, at the 6th year, we start earning money because we have recovered our investment, and because of the savings that we are getting with this PV array, we start earning money and saving money. And at the end of 20 years, my positive balance is 17, almost $18,000.